What are differential equations? Let's start with a definition. Differential equation relates a function to its derivatives. A few examples might be something like y prime of x is equal to y of x. So here, the derivative of y with respect to x is equal to y of x itself. We could also have higher order derivatives. For example, we could have y double prime of x is equal to minus y of x. We could have something even more complicated, like y double prime of x minus 3 times y prime of x minus 10 times y of x is equal to sine of x. So here on the left-hand side of the equation, we have the function y, the dependent variable, and its derivatives. And on the right-hand side, we have another function of x, the independent variable. But many of these seem quite artificial. So let's try and see if we can find any motivation behind constructing such equations. Let's take the second equation, where we have the second derivative of y is equal to minus y. It seems quite arbitrary, but is it really? Could we find something like this in the real world? Most people, when they start with differential equations, feel that it's a completely new topic that they haven't dealt with before. But in fact, many have encountered that indirectly, even without knowing it. I feel one of the best examples is Newton's second law. What it says is that the net force on an object, F, is equal to its mass m multiplied by its acceleration a. I like to rewrite it as a is equal to F over m, because here on the right-hand side we have the cause, which is the net force on an object, and on the left-hand side we have the effect, acceleration, meaning that net force on an object causes that object with mass m to accelerate. But what is that net force? Well, it all depends on the situation. Suppose we have a scenario where mass m, initially at point 0, is pushed to the right. However, that mass is attached to a spring which resists any displacement from its initial position. Now, if that mass m is pushed to the right by r units, then the force resisting that change is going to be equal to minus kr. Now that's of course a model of how springs work, and it's not an ideal model, but it's a pretty good approximation. And what it basically says is that the force is going to be proportional to the displacement r, and it's going to be acting in the opposite direction to that displacement, which is why we have the minus sign. What we can do now is plug this into Newton's second law. So initially, we had A is equal to F over m. We can now replace F with minus kr. The next thing we can realize is that acceleration A is actually just the second derivative of displacement with respect to time. So we can put that in the left-hand side of the equation. And now what we see is that we actually get almost an identical form in that second equation that we had in the very beginning, which shows that these kinds of equations can very easily appear in the real world. Before we start tackling differential equations, it's important to understand what we mean by solving a differential equation. If we just go back for a little bit and think about conventional equations or algebraic equations, in those equations, solving an equation typically means finding a number or a set of numbers that satisfy that equation. For example, if we have an equation x squared is equal to 4, one solution to that is x is equal to 2. And how do we know that this is a solution? Well, we can simply plug that into our equation. Because 2 squared is equal to 4, that means x is equal to 2 is a solution to this equation. With differential equations, we go one level up. What we do is we solve for functions that satisfy the equation. Remember, in differential equations, we have functions and their derivatives. And functions are something that depend on some other variable, the so-called independent variable. So we might have an equation like this, for example. Y prime of x is equal to y of x. So here, y is the dependent variable, and x is the independent variable. Solving such an equation means finding an expression for y of x. Now I claim that a solution to this equation is y of x is equal to e to the power of x. How can I prove something like that? Well, I simply plug that into the equation. For the left-hand side, I have to differentiate this expression, that is e to the x, and of course the derivative of e to the x is e to the x. If I now compare that with the right-hand side, which is the function itself, e to the x, I find that both sides are equal, meaning that e to the x satisfies this differential equation, meaning that y of x is equal to e to the x is a solution to this differential equation. To summarize, differential equations relate functions and their derivatives. Many phenomena in the real world can be described by differential equations. Solutions to algebraic equations are numbers, and solutions to differential equations are functions that satisfy those equations.